Hello all. The aim of the experiment is to determine the numerical aperture for an optical fiber. This is the link to the Amrita virtual lab where we can find the simulator to perform this experiment and the relevant theory. Optical fiber. The basic of the optical fiber is that it is a transmission medium which allows light to travel from sender to receiver with the help of total internal reflection taking place inside the fiber. Total internal reflection is the phenomena which takes place when light tries to travel from higher refractive index medium to lower refractive index medium. Now, this is the core part and this is the cladding part. Core has a refractive index greater than that of the cladding so that TIR can take place inside the core. So, the light has to be retained inside the core of the optical fiber so that it can be received faithfully at the receiver end. The diameter of the core is less than that of the cladding. This is the cut section of the optical fiber in which two rays are shown. Ray 1 undergoes TIR and is received faithfully, whereas ray 2 could not undergo TIR and it is lost in the cladding part. Now, look at this figure. The light incident has an angle of incidence I. The medium we have taken as air, so its refractive index has been assumed as 1. The angle of refraction at the core air interface is theta and the angle of incidence at the core cladding interface is theta dash. Now let us reach to the condition of TIR and then to the numerical aperture of the optical fiber. As per Snell's law, refractive index of medium 1 multiplied by sine of the angle of incidence in the medium 1 is equivalent to the refractive index of medium 2 multiplied by the sine of the angle of refraction inside the medium 2. So n0 sine theta is equal to the n1 sine theta. Now n0 is equals to 1, so sine I is equals to n1 sine theta. Now what we have to assume, we have to get into this core cladding part. Now at the core cladding interface the angle is theta dash. Now consider this angle theta dash such that the angle of refraction in the cladding part is 90 degrees. At that point the refracted light is basically grays the core part and it remains inside the core itself. So it is not going to get into the cladding part and is not lost. So this is actually the boundary condition where the angle beyond this angle would retain the light inside the core part. Otherwise it would be lost in the cladding. So considering that condition into account, n1 sin theta I, that sin theta c, means I am trying to apply the Snell's law at the core cladding interface where the angle of incidence is theta dash at the condition when the angle of refraction is 90 degrees. At that point of time the incidence angle is known as the critical angle. So the critical angle is basically the angle of incidence in the denser medium such that the angle of refraction becomes 90 degree at the second medium. So considering that condition into account, I get this equation using the Snell's law. So my sin theta dash becomes n2 by n1. Now let us get to the numerical aperture. What is the definition of numerical aperture is? The maximum angle of incidence at the air core interface such that my angle of incidence at the core cladding part becomes critical angle or greater than that and that maximum angle of incidence is termed as the numerical aperture. Is the numerical aperture basically. So that maximum angle of acceptance gives me the acceptance angle, and sine of that maximum angle gives me the numerical aperture. So what is my numerical aperture is the n0 sine theta im. What is this im? The maximum angle of incidence at the air core interface such that inside the core part at the core cladding interface my TIR can take place. So Na is what? N0 sine theta im. This is the definition of numerical aperture. Now this is equal to what? N1 sine theta, which is taking place at the core part. Now as per the triangle law, theta angle is equivalent to 90 degree minus theta dash. So I can write it down like this, which I can write it down like cos of theta. Now numerical aperture can be written as n1 cos of theta dash, where theta dash is the angle of incidence at the core cladding interface. Now this can be further written as 1 minus sine square theta under root. So n1 under root of 1 minus sine square theta. Actually they have used the subscript c to show the critical angle, but any angle greater than the critical angle can be termed as theta dash, which fulfills the condition of TIR. So this is my condition of TIR and numerical aperture, and as per this numerical aperture we can get the angle of acceptance, which is sine inverse of this value, and any ray of incidence which is within this limit, within this cone of light gather, will be total internally reflected, or I can say that it would be faithfully received at the receiver end. Now before jumping off to the observation table, I will go to the simulator first, and then I will try to show you the observation columns. Now this is the simulator which is available at Amrita Virtual Lab. This is the bench, and these are my apparatus which have to be kept on the bench. Now I will begin from the output part first, putting the output unit at the leftmost end. This output unit tells the current. Then we will be putting the fiber stand, the detector unit, the concentrator, the emitter, and at the end fiber. This is the optical fiber. After putting all the apparatus on the bench, we will press the start button. Now this is what it looks like. Now we are looking at the detector end. We are here and we are looking at the detector end, and we will be observing the ray that is being detected. Now we will press the switch on button, and we can see the spot of the light that is received. We can choose any one of the glass or plastic glass fiber, or a glass fiber, or a plastic fiber, and we can choose any one among the three options of the laser: red, green or blue. Let us take a blue one so that it can be seen clearly. Now this is the Z distance, the detector distance. What does this distance show? This is the distance between the detector and the optical fiber. This is the distance between the detector and the optical fiber, and it has to be kept at 4 mm. You can keep it at any distance, but for this point of time we are keeping it as 4 mm. Now the distance x is basically the distance from the central point. We are going to move this detector in the left and the right direction with the help of the screw gauge, and we are going to move it from -8 mm to +8 mm. with the help of this slider or with the help of the screw gauge buttons. As I increase the detector distance from -8 to +8, I get this type of graph. Now what the student has to do is, student has to vary the distance at an interval of 0.5 mm starting from -8 mm and move towards +8 mm and keep on recording the current at the output unit in order to draw the graph. So what we have to do is, we have to obtain the graph with the help of this current and the distance x from leftmost point to the rightmost point, and we have to obtain this graph. Now this was the type of observation table that we used. We recorded the distance x from -8 to +8 and the current I in microamps by looking at the output unit. With the help of these values, we drew a graph like this. So we obtained the graph, and from the graph, what are we going to do next is, we have to record the maximum value and Imax by 2.71. So we have to mark these points. We have to take this point and we have to take this point. From these points of intersection, we have to obtain the points at the x-axis. The distance between these 2 points is 2r, where r is the radius of the spot received at the detector point. After obtaining all these values, we have to use this calculation for calculating the numerical aperture and the acceptance angle. D is basically Z, which is 4 mm. Radius of the spot has been obtained from the graph. Using these two values, we will get the numerical aperture with this formula, and by taking sine inverse of that value, we will get the acceptance angle. So this is the basic working principle working and observations and calculations part of this experiment.